Our next talk, through the magic of a lot of magic and honestly the amazing team that we have helping put this on, is going to be a remote talk due to some travel challenges. So we're going to make it happen because we love making magic happen. I would also just take a minute to thank some of the sponsors. We have some amazing sponsors. I won't go through them all right now, but I'll slowly go through them all. Platinum sponsors, we have Charles River. I know some folks working at Charles River. Amazing place, and so happy to have them here as a sponsor. And of course, Nearform, got my t-shirt on, is the sponsor, a platinum sponsor of NodeConf. You know what? Nearform is always hiring somewhere. So go and check us out at the booth. Go and talk to the folks, the talent team, the people team. They'd love to know a little bit more about you, and they would point you in the right direction if you're interested in doing some amazing professional services and getting to work on open source, some of the amazing things that we do at Nearform. I'll talk more about that later. So I know that our next speaker is online, ready to go. Her name is Tamar Twena. She's a systems architect at XM Cyber. Can we give a big round of applause to our next virtual speaker, Tamar Twena? And one last thing before the round of applause, if we have time for questions at the end, you're going to need to give the microphone because she's dialing in remotely. So if there's questions, just make sure I give you the microphone before you ask the question. Thanks, everyone. Big round of applause for Tamara.
Hey, everyone. I hope that you can hear me.
Yes.
I am really excited to be here at NodeConf. And my name is Tamar. And welcome to my session. So we're going to talk today about V8 and architecture of V8 and how all of that is going to affect your server performance. So I'm going to start with introducing myself. My name is Tamar. Actually, I'm really passionate about Node.js, and my interest in that technology started several years ago when I founded a startup of my own. And I wrote the entire backend in Node. And from that point, I started to get really deep into that technology. And it's really fascinating and explored a lot of stuff. So you can follow me on those links. And you know what? Let's stop wasting our time. Let's get going. So V8. What is V8? So V8 is an engine to run JavaScript. It can run JavaScript and WebAssembly. And originally, it was written for Chrome. By the way, it's cross-platform. It is running on all operating systems. And it is used in multiple platforms today as it is super cool and super fast. And of course, one of the platforms is Node.js. So that's the architecture of Node.js. And V8 has a very crucial role in Node.js architecture. So actually, V8 has two roles. So one role is to do the code parsing and execute the code. All the JavaScript code that you're writing is parsed in V8. The other role that V8 has is memory management. So in this talk, we're going to talk only about code parsing and not about memory management because, I can spend talking 3 hours about memory management. So we're going to focus on the code parsing part. Okay, so actually JavaScript and Node.js are really, really popular. And well, in that case, V8 have a really hard task, which is to be a really super fast interpreter for a language which is dynamically typed. It is dynamic typed. Why that is hard? So actually, there are, let's say, two types of languages. We have languages that are compiled, and there is a compiler that takes the code and translates into machine code. And we have languages that are interpreted, meaning that we have an interpreter that takes the code and translates it into machine code, translate high-level code into machine code line by line. Other two, families of languages that we have is dynamic type languages and static type languages. And dynamic types, all of the types are being, all of the types are determined in runtime, and in contrast to static types where the variable types are determined in compile times. So compilers have huge advantage over interpreters. For example, execution overhead. Interpreters can see one line every time. Compilers can see the entire scope. Compilers can use memory much more efficiently. Compilers can perform optimizations which are related to the specific operating systems that they are running on. And interpreters usually don't do that. So also dynamic type languages do some, let's say, tricks in order to determine the types in runtime. They're doing runtime checking. They're doing something called dynamic dispatch when they're executing methods, which is on runtime, understanding which method you need to execute. And choose a method in runtime. That is really hard. So I actually think that maybe the turtle is going to make you a little bit laugh. But in most cases, what's happening is that compiled languages are much faster than interpreted languages. And of course, like the typing dynamic via static is also like a factor here. And, JavaScript is in the turtle section. It uses interpreter and it is dynamically typed. So V8 have a hard task here in order to make it work and be fast. So to make it fast, we have one interpreter and two compilers which are coming to the rescue. We have Ignition interpreter, we have TurboFun compiler, and we have the Sparkplug compiler. So now we're going to talk about the code parsing pipeline and how it's working, and actually what's happening in your software in runtime. What's happening when your code is running? Okay, so here is the pipeline of the code execution. And the first phase is parser and AST. We have the JavaScript code. We have a parser. Parser is parsing the code into token and turn them into an AST, an abstract syntax tree. So this is an example of an AST of a very simple code. And as you can see, that's like the output of the AST. And here you can see a structure of a tree in which every, let's say, token or part of our code is being represented. Now let's talk about the Ignition interpreter. So Ignition interpreter is actually taking the code line by line and translating it into bytecode. By the way, there's a JVM beneath all of that translates to machine code, but Ignition interpreter is translating line by line into bytecode. Then now let's talk about the TurboFun compiler. So what is the TurboFun compiler? So every code that is running for multiple time is marked as hard code. Let's say I have a function which is running 1,000 times. So that function is being sent to TurboFun, and TurboFun is generating optimized machine code. And send it to Ignition. So the next time that function is going to be executed, so the machine code that was generated by TurboFun is going to be executed. Okay, so we need to help TurboFun work fast. And in order to help him work fast, we need to use less input type variations in our code. What does that mean? So now I'm going to show some TypeScript examples, but all of this is related to vanilla JavaScript. The TypeScript syntax is just to make us all understand. Okay, so what's a monomorphic function? So I have this function. That function, every time it executes, would receive one parameter, and the parameter type would always be a number. That would never change. Polymorphic function. So that is that situation is not very good, but it's still okay. So this function has one parameter, but it can receive while executing once it's receiving a number, and the other time it is receiving a string. And that's a megamorphic function. That's a situation which is really bad. So that function receives one parameter, but that parameter can be, once it can be a number, and the second time it can be a string, and the third time it can be an object. You get it. So one of the assumptions that Turbofan is doing in order to generate the machine code for a function, for example, is what type of the parameter the function will receive. So when this type is changing, well, what's happening is that Turbofan usually release the binary that it is had generated. So in that case, that is a really bad case, and that can really harm your performance. That can harm your application performance. So that is a situation where you don't want to arrive to. When you have its function, always make sure you're transferring the same types. So now we're going to go back to our pipeline, and now let's talk about optimization and de-optimization. We're going to talk about all of these. So what that means. So ignition interpreter, as we said, if we have the code that is running for multiple times, large n, let's say n equals 1,000. So that code is marked, is transferred to Turbofan. Turbofan is creating an optimized binary, and from that point, ignition is using that binary. But there are some assumptions. By the way, one of the assumptions is if for a function, which type the function would receive. And if that assumption breaks, what's happening is that ignition is releasing that binary. And in that case, the code is going through a process of de-optimization. And that is a process that can really harm your performance. Let's see an example of a de-optimization. We have here a class person. That class have two properties. It has a name and an age. And you see there is a function here, get age. All right, so now, in real life scenario, your server is running and that function executes a lot of time to simulate. I took like a really large loop. And what we're doing here, we're creating an object, and then we are executing this function with a person object that has two properties. Okay, after X iterations, Turbofan would create an optimized binary. Now that's the de-optimization. So what's happening here? So we are creating an object, a person object, and then we're adding a dynamic property, as you can see, salary. In that case, the shape, the hidden class, which is called actually the shape of the object, is changed. So right now there is a different hidden class, there is a different shape, which is attached to that object. Now get age is getting this object with a different shape, and that is a different type. And in that case, the binary is being released, and we're in a process of de-optimization. And that's something that can harm your performance. Now let's do a small benchmark. Let's see what's happening like with time measurement when we do have de-optimization scenarios. Okay, so we have a really simple code here. As you can see, we have a function that receives an argument. What we're doing is just adding one argument to another, and then we're going to do like one large loop. We're simulating the activity of a server that's running, and we're always transferring a string. And now we're going to do de-optimization. I chose a random index, and in that random index, I transferred a number. In that case, Turbofan has already generated a binary which is fit to a string, but then it receives a number, and that binary is going to be released. So if you're comparing, like I was running that and doing measurement with a loop of a size of 10,000 and 100,000, and there is a huge difference. Meaning that when the numbers are big, as long as much de-optimization that you have, your code is being harmed for that, as that is not good. Now we were talking about it's a lot of vanilla JavaScript, but all of you might thinking, all right, so we're working a lot with TypeScript. We're like we're at least safe in development time. When we're developing and we're working with TypeScript, Then development, we're always make sure that we're transferring the same types. But for example, I want to, to have your attention about union types in TypeScript. Like that is a situation in that function that, maybe I guess that a lot of TypeScript developers are using union types. And union types are, case when you get to a de-optimization very fast. Because according to that, you're able to transfer to your function, you're able to transfer a string, and then you're able to transfer a number. And in that case, Turbofan would generate one binary, and generate, release it and do the optimization and generate another binary. So that's, for example, a situation when TypeScript enables you to get to de-optimization scenarios. So keep that in mind. And, when you're working with TypeScript, even in TypeScript, it's not like protecting you 100%. And also make sure you don't do things like that. That could be like huge flaw and can get to a de-optimization scenario. Okay, so another thing that I would like to talk about is finding performance killers. So how can we know if we're getting to de-optimization scenarios? So there is a hidden flag in Node.js, which is called trace ops and trace deops. So that flag, when you're running your program with like those flags, you're able to see a log, you're able to see a trace that will show you exactly whether your program is going through de-optimization scenarios. That is really cool. And I found personally a lot of things, a lot of performance killers and a lot of spikes in runtime using that. But, that's, for example, I ran this for, the add function type. And, that is an example of the logs that I got. And you can see very clearly that we have a de-optimization here. We had a binary created by Turbofan. That binary was released. And then, the whole optimization process is starting all over again. Okay, so now after we've talked about our pipeline, so let's go back to, the code pipeline. We've talked a lot about de-optimization. Let's go back to the pipeline. I would like to give you a little bit of spoilers. So that pipeline wasn't perfect. That pipeline needed improvement. So what needed improvement? So as you can see, all of those were weak scenarios in that pipeline. So there are scenarios like application start and, like dynamic environment with a lot of de-optimizations. But what is happening here at the end, we have the ignition interpreter that is working line by line and translating your code. And Turbofan helps you with hot code that is running for like a lot of time, that is being invoked for multiple times. So we can say that, the pipeline that worked was really good when our application was already warm, when it was running for a lot of time. But, in like cases of server startup and in cases when our application was not, let's say, was not warm yet, so this pipeline was not good enough. Okay, so that pipeline had turned into this. Okay, now look at this like extra adding that we had here. So we have here the Sparkplug compiler. So the Sparkplug compiler, the job of the Sparkplug compiler is when the ignition is translating the code line by line. So the Sparkplug is generating machine code for every line that the ignition has created. For every bytecode, so the Sparkplug is generating machine code on the fly. So in order to understand what is the change from the previous situation, so that's what we had before we added Sparkplug. So as you can see, we have here two functions. The names are not really sophisticated. Do stuff 1 and do stuff 2. And in that case, we're going to generate optimized machine code only for do stuff one because it is like running, it is becoming as a hot code because it is running for a lot of time. It is running, it was invoked, it was executed for a lot of time. So turbofan is going to generate an optimized machine code for do stuff one. Now, when we have Sparkplug, we're going to have machine code from the beginning. So do stuff one is the code of do stuff one. So a machine code is generated by Sparkplug for both of them. And only after, only in the loop when do stuff one is invoking a lot of times. So we have machine code, which is generated by turbofan and is more optimized. But we have machine code for all this, code from the beginning in contrast to what we have previously. So you probably think to yourself, all right, so Sparkplug doesn't have a lot of time to work. So it receives in background every like bytecode line, and it's working in background to generate machine code. It doesn't have a lot of time to generate optimizations, and you're right. But Ignition is doing a lot of work, let's say, for Sparkplug, and it's already like handling the variable resolution and handling like the parentheses and handling all of this. And so Sparkplug is only generating machine code on the fly, not optimized after Ignition has parsed everything. So what this improvement has gave us. So I have ran, for example, a server that I had. We've talked about startup, and startup is a weak scenario. As we said, in application start and server start, the code is not hot. The code is still like the application is still being warmed. So actually, when we're going forward in Node.js versions that have the new V8 version, we can see that the performance of the server startup has improved by around 30%, around 30 to 40%. And that's a lot, and that's like a huge improvement. Okay, after talking about code parsing pipeline, another thing that we're going to talk about is class initializations. And in order to talk about class initializations, we need to understand how JavaScript objects are actually built behind the scenes. Okay, so that's also like an evolution. Once upon a time, just kidding. So that was the initial version of it. Okay, so that was the JavaScript object. That was the initial version. So we have an object here, as you can see, with property X and property Z. And X is pointing to, a set of configuration, writable, enumerable, configurable. But what's important, it was pointing to the value. As you can see, the value is something like the value was represented like this. As the object itself, the memory allocation of the object was containing the properties, and the value was in like this set of configuration properties. But in that case, just imagine that I have a million of objects with two properties, X and Z. And in that case, this structure is going to be duplicated a million times. Like and when you're thinking about memory management, that is really, really inefficient. So, V8 had introduced the shape. All right, so what is a shape? Right now, the object structure is different. So in the memory allocation, we have the values of the object itself. As you can see, X has the value 1, Z has the value 2. So we have the values of the object. And then this object was pointing to a shape. And that shape has the properties X and Z and a set of configuration properties. But another thing that is happening here, so so in the shape itself, there is the offset of the location of the value in the memory allocation. So when we want to fetch the value of property X, we go to the shape, we go to the offset, then we go to the memory allocation, gets the value in that offset, and then we return the value. But there is a little bit of lookup here. Go to the property, to the offset, to the object, and then to the memory allocation. And that lookup was expensive. That like fetching the fetching the fetching the offset itself every time from the shape was very expensive. So what was done here is using a technique called inline cache. Inline cache is a technique that is being used in compilers in other languages, but that is a set of instructions which is saved in a cache to fetch the offset much more quickly. Okay, so now let's go back into monomorphic functions and polymorphic functions. So we've talked about all of those like functions when we're thinking about like the turbofan and what's happening to the binaries that the turbofan is creating. But what's happening to the inline cache when we're like playing with the types, when we're starting to transfer multiple types into one function and we're not sticking into the same type. All right, so we have the inline cache. Imagine that the inline cache is a table in memory with a limited number of entries. So we have the function get x. We need to get the property x, and it's getting an object with one property. This object has one property of x and one shape. Then I'm transferring to this function another like object. That object has a different shape. In that case, our inline caching has two entries. All right, then I'm continuing to playing with the types. You can see now I'm transferring another object from a different type. Now I have a property B. The type of the object is always changing. And then, I have 4 entries. I'm still in a polymorphic thing. I'm still okay, kind of. But then I'm going into megamorphic. What's happening here? Because that is, a table in memory. That's a cache in memory. Then, at that point, entries are starting to erase each other, to override each other. So, this entry with this shape, with the like property D is erasing, let's say, the first one that we had. So we have like, in that case, the inline cache optimization is really harmed. So that is another, motivation for you when thinking about types to always transfer the same types to your code. So until recent V8 versions, inline cache was not implemented for class fields. So V8 was more working in like implementing the inline caching for, let's say, regular objects instead of classes. But that was fixed in latest V8 versions. So let's see like the time differences when initializing when running a code that is working with classes in like previous and new Node.js versions that are using new V8 versions. So that is our code. As you can see, we have a class person. Again, we have that property age, and we have a function get age. And that is the loop that we're doing. We're initializing the class, and we're calling get age. And as you can see, the initialization, we're seeing like improvement at, I think, around 30% in working with class properties in latest V8 versions. Okay, so we're about to wrap up this section. So what's in it for me? First of all, when you're working, always make sure you advance the libraries that you're using, your Node.js versions. Always make sure you're advancing the infrastructure that you work with in order to get all the latest optimization. Second, TypeScript. All right, it's not perfect. It's really far from perfect, and we saw the union type stuff, which bring us straight to the de-optimization scenarios. But it can still help you, a little bit. It can still protect you on development. It can still protect you on development and help you to transfer the same types for your function. remember, you're working with TypeScript, but you're always deploying vanilla JavaScript. Always deploying vanilla JavaScript. Avoid weird things that you can do in TypeScript, as TypeScript enables for us a lot of things like union types that will be able to enable you to transfer different types into your software, into your functions, and make your performance go crazy. So avoid those. Always, for example, protect your schema. When you're working, another case when we can think about is when we're sending a request from the front end. Make sure your schema is always correct, and always, even one property can create a different shape and can create runtime spikes. And I guess that was it for me, as V8 is a really fascinating subject, and I hope you've enjoyed it. You can, of course, follow me on those links, and continue to have a great conference, and have a good day.
Big round of applause for Tamar. Thank you so much. Wow, what an amazing talk. Oh, Tamar, so happy that you're here. I promised you that we're going to do live questions, but I don't think we're going to have time to do it. I'm going to go on to the next talk. I just want to acknowledge that in light of the current events in Israel, Tamar couldn't be here today. So I don't think that was a choice. I think that was something forced upon her. So thank you so much for making this happen. Thank you, Tamar. Have a great day and enjoy the rest of the conference. Thank you so much.
Thank you.